Welcome to this video on Excel's trend function, ordinary least squares, and multiple regression with me, Duncan Williamson, 15th of March 2024. Using the trend function for multiple regression, the syntax of the trend function is known y's, known x's, new x's, and constant, and the new x's and constant are optional. The known y's are all of the dependent variable values in your dataset. The known x's are all of the independent variable values in your dataset, and notice you can have one, two, or more independent variables in your trend function analysis. New x's, the new x values if you wish to use trend for forecasting, and setting the constant to 0 or including it in your regression equation, otherwise you leave constant alone. What we can deduce from the syntax of the trend function is that we can use it for making linear predictions for ordinary least squares calculations. That's within the boundaries of the known data, and for projections beyond that. The new x values setting the constant or intercept term in your formulation to 0 or leaving it as normal. I'm setting up a partial scale example. The full dataset comprises 1470 rows of data, which is 1 row per employee. But for demonstration, I randomly selected just 100 rows of data comprising x1 age, x2 tenure, x3 hourly rate, 4 daily rate, 5 the monthly rate, and then y, the dependent variable, monthly income. Now, I had sorted the main database into random order and then extracted 100 rows by copying what was now the top 100 rows of data, or I could have chosen the bottom 100, or any 100 rows of data for that matter. And this is what we see in my Excel file on the Pay Analysis 100 Rows worksheet. I use my trend analysis on the top 8% of the data, leaving 20% of the data to be used as training data. Again, I've used the liness function here to help me to demonstrate what the regression coefficients are and the t-statistics. This is with a constant, which are confirmed down here, and without a constant, which I just show here. So we have the monthly rate, the daily rate, the hourly rate, tenure, and age. And there's the intercept. That's obviously with a constant. With no constant, here we see the monthly rate, the daily rate, hourly, tenure, and age, and a constant that doesn't exist. The t-statistics, I've calculated them from no constant version of this, which I don't show here, but you calculate it by dividing the beta coefficient by its standard error. You can see clearly it's this one. What we see here is that how many significant variables do we have in this model? No, no, yes, yes, and yes. 3 out of 5. In the with constant example, no, no, yes, yes, and yes. Again, 3 out of 5. How do I know they're significant? Because they're less than -2, greater than 2, with a data set of 80. Since we've used the training and testing technique, we can check on the quality of our results to some extent by finding the standard deviation of the residuals as between training and testing. And we expect them to be the same or very similar to each other. They aren't really, they're quite a way away in both cases. Predictions 1 and 2, training standard deviation residuals, and the testing residual standard deviation. I'll come back to the means shortly. Here's an extract of my 100-row data. In the order you can see them. And here's my prediction 1 using the version with the constant. Without the constant, here are the values, here are the residuals, and it goes on for 80 rows, and then we repeat that for the testing data. If you're working along with me then, just go and open the Excel file and do this by yourself, and then you can check that your own work is the same or very similar to mine. If you want to select your own sample of 100 by using your own version of the random numbers, then your answers will be different from mine, similar but different. As soon as you include a randomization of the order of the data, your answers will be different. Let's have a look at the graphs then. They're also on the pay analysis 100 rows worksheet, along with the data and all of the workings and results. A couple of things to say. Employee number and their results. I've got the monthly income, the blue dots, and the prediction, purple dots, all in the same graph. This is for predict 1, which includes the intercept value. And here's the residuals, histogram of the residuals, and you can see it's positively skewed. At least in theory, we'd like the residuals to be normally distributed. They aren't. Not in this small sample anyway. And similarly for prediction 2, the blue ones again are the actual monthly income, and then the purple ones are prediction monthly income 2. Again, compare. You can see, just as let me point it out, there appears to be, there we are, there is one value that's, is it fractionally below 0? Right on the border anyway. And the residuals, the distribution of residuals, again, positively skewed, not normally. Maybe it's a fraction more normal than residual 2, but you need to calculate the skew coefficient to confirm that. A bit of stats now. Why would you run a regression analysis by asking for the intercept term to be set to 0? Well, in regression analysis, setting the intercept term to 0 is a deliberate modeling choice that can be appropriate under certain circumstances. And the intercept term in a regression model represents the expected value of the dependent variable when all the independent variables are equal to 0. Typically, the intercept is included to account for the mean value of the dependent variable that isn't explained by the predictor. And there are situations where setting the intercept to 0 is meaningful. Theoretically, if the theory or the nature of the data dictates that the relationship between the variables should pass through the origin, i.e. when all independent variables are 0, the dependent variable is also 0. And it's appropriate to force the intercept to be 0. For example, if you're modeling the relationship between the amount of a chemical and its reaction rate, it might make sense to set the intercept to 0 because no chemical should mean no reaction. And in some models, the scale of the measurement inherently starts from 0. For example, if you're predicting sales revenue based on units sold, then it's logical that when no units are sold, 0 units, the sales revenue should be 0. I just ran a regression analysis with and without the intercept, and one result I got was 7479.36 with an intercept and 7119.67 without an intercept. So what can I conclude from that? With the intercept, the model includes a baseline value for the dependent variable when all predictors are 0. And without the intercept, the model assumes that the dependent variable is 0 when all predictors are 0. The coefficients in these models represent different relationships due to this fundamental difference in model structure. Compare the fit of the model with and without the intercept, and this can be done using various metrics such as R-squared, adjusted R-squared, the root mean squared error, Akaike information criterion AIC, or Bayesian information criterion BIC. A better fit might suggest a more appropriate model for your data. However, remember that fit isn't the only criterion. Theoretical soundness is crucial. By the way, I don't include any of these in this discussion, in this video. Analyze the residuals of both models, and ideally, residuals should be randomly distributed with a mean of 0, and systematic patterns or biases in the residuals can indicate model misspecification, such as the inappropriate exclusion or inclusion of an intercept. And I mentioned very briefly the standard deviations of our two models. Let's have a look at the mean then. We've just been told that we should have a mean of 0. Well, we don't, but they're not a million miles away from each other, are they? This one's slightly more than this one, but they're very close compared to the standard deviation anyway. And remember that we're working on just a small sample of data here, and the means are very close to each other, though, aren't they? That's my introduction to the trend function in Excel, where it may be the first time you've ever seen it applied to multiple regression. It does the same as LinEst, the same as the data analysis toolpack, and the trend line. However, it doesn't give it any supporting statistics or coefficients or anything like that. So if you just need a quick review where you want to use the training and testing data and so on, nothing wrong with it at all. Final point, it's linear, not curvilinear, not quadrilateral, not exponential, linear only. There you are. You can download the Excel file with all of these workings and the 1470, the full database, together with all workings from the link in the discussion. But there you are. That's it from me, Duncan Williamson. Thanks for watching, and I'll see you in the next one.